buenos días a todos. Muchas gracias por acompañarnos el día de hoy. Me presento. Soy Juan Alberto Alcántara Cárdenas y a nombre del Centro Interdisciplinario de Investigaciones y Estudios sobre Medio Ambiente y Desarrollo, les damos la más cordial bienvenida a esta sesión de la Cátedra Patrimonial en Medio Ambiente, doctor Héctor Mayagoitia Domínguez, del Instituto Politécnico Nacional. En esta ocasión contamos con un excelente ponente, el profesor Feng de la Universidad Tecnológica de Química, quien nos presentará la conferencia High Performance Oxygen Electrode Electrocatalysts Derived from Layer Double Hydroxides. El doctor Yongjun Feng, le agradecemos mucho que nos pueda acompañar en esta sexta edición de la Cátedra Patrimonial. Al igual, saludo al doctor Luis Astudillo Wong, que nos va a estar ayudando en la parte de preguntas y respuestas. Me permitiré leer una breve semblanza del profesor Feng, el cual es director del Departamento de Química Aplicada de la Facultad de Ciencias y también y en la universidad también es profesor de la Universidad Tecnológica de Química de Beijing. También el doctor Feng realizó su doctorado en Ciencias de Materiales y Química en la Universidad de Blaise Pascal, en Francia. En 2007 realizó un postdoctorado en el grupo de electrocatálisis en la Universidad de Poitiers, en Francia, donde ha explorado electrocatalizadores de metales no preciosos para la reacción de reducción de oxígeno, esto con el profesor Nicolas Alonso Bante. Bueno, posteriormente vamos a ver la dinámica de esta sesión. Bueno, la dinámica de esta sesión será la siguiente. La presentación del profesor Feng está programada para 45 minutos. Cabe aclarar que la presentación va a ser en inglés. Posteriormente, bueno, pues daremos paso a un espacio de preguntas y respuestas. Las preguntas se harán a través del chat de la transmisión y le solicitamos, por favor, que nos digan su nombre y la adscripción o lugar de origen. Profesor Feng, le dejo el micrófono. We can start the presentation, Professor Feng.
Okay, thank you. Okay. Thank you, President Dr. Juan. My name is Yongjun Feng. The family name is Feng in Beijing University of Chemical Technology. It's State Key Laboratory of Chemical Resource Engineering. Today, good morning, everyone. Now it's in time in China is about 1 o'clock in the morning. So today I show my title is the high performance of oxygen electrode electrocatalyst derived from lead double hydroxide is LDH. Here I show the about 4 parties. First, we just the brief introduction about the BUCT and the laboratory. The BUCT of Chemical by University of Chemical Technology is in the center of China, the capital of center of Beijing, the capital of China. In China, more than 2,000 universities, is about the top 50 to 60, about 25,000 students, about 2,000, more than 2,000 staffs. In chemical engineering, the top 5 and the top 18 in chemistry in China. Here is about in China. There are 3 the capitals. One is in center, other one is the outside. It's there for university. About in center, about it's 10 kilometers to the center of Beijing. So about the chemistry of College of Chemistry, the beginning is Beijing University of BUCT was built in 1958, so more than 60 years in China. After to the applied chemistry School of Science, or in 2019, is the College of Chemistry. So here about 120 the staff in the College of Chemistry, more than 51 for professor, 51 associate professor. Here about the chemical resource engineering is a static key laboratory of chemistry and chemical engineering research in China. In China, more than is about 7 the static key laboratory of the chemical engineering. The CRE is about the top 3 in China. So in here, about 3 branch of laboratories in the collection, chemistry of inorganic functional materials, or the Greek chemical engineering and the process intensification, or efficient use of polymer resource. In the College of Chemistry, about recent 5 years, so we can see the every year the funding from the government, from the company. So almost is more than 500 million RMB, RBM. So also in 5 years, publication or patents. The publication is about 500 every year, or patents almost 70 to 80 to 30 in the national invention patents. So, and also ESI in China in the chemistry in BUCT is in 2018 is to the first the 1001 the ESI of the chemistry, but also in this year it's very steadily improved. This is our team of personally the group. So we have there's about 10 the people inside in the team. Here of more than 10 the team in the CRE, the state group. So are the students. It's more than 12 PhD students and 55 the master students in the team. So we can work on the FEMR or applied FEMR, also the engineering diploma. So this one just me at the beginning, the Dr. Duan is introduced. So it's my the brief introduction. So here is that's why I know the Dr. Lucy, the Professor Lucy, because my postdoctor in the University of Poitiers in France. So I in the group of professor also one group. So that's why we have I think last time is 2017 or 18. I come to the Mexico for the meeting. In my small group, so work on the 4 topics. The first one is spheral aluminum-based catalyst support. So this one is especially for enduring application. Second one is multifunctional the materials. Is based on LDH. It's lead double hydroxide. The third one is the porous or the sorption materials. Also, it's no pressure metal electrocatalyst for fuel cell and neutralizer. So we also think about how to efficiently use chemical resource. So about me, more than is about 120 the peer-reviewed papers or there are patents. Here have some information is about in the problems. So the one is there are some paper or some in the situation. So one is in our work. We work is on the paper, the patterns. Also, we work on the project, the technical, the project platform. So the one is one in outside for their double hydroxide, RDH. Also, is for aluminum. It's a collaboration with the company. So we can produce the diameter 0.5 to 3 micrometer, the aluminum for the catalytic support. So we use the industry, the company. Okay, the some students. The one student is Hai Hong Zhong. I think that Pretty Lucy knew her. So when she get the degree of PhD, so he published more than 12 the paper. The other one is the Chen Zhang. Also, because she worked almost 1 year in the Pascal University in the center of France. Okay, in the slides about this topic, I think most people know about in the world or in the China, the faster energy or the clean energy, because the people increase publication increase or the faster energy crisis and pollution. So we need to develop the chemical, the clean energy. So inside the chemical, the process play an each role in the energy conversion and storage technologies. The fuel cell, electrolyzer. So the one in the world or in the China, in the government is pay a lot of money, a lot of the funding and the time to develop the chemical energy to electric energy. So one is the fuel cell. Fuel cell is about the hydrogen energy. So it's very clean. So so we need to develop how to produce the hydrogen or how to use the hydrogen energy. So the fuel cell almost one of the best one for the hydrogen energy. How to produce energy? So electrolyte of water, the green hydrogen. So we need both the fuel cell and also electrolyzer. We need oxide, electrode electrocatalyst is the key one. So here we need also in the background. This is why at the beginning is in my postdoctoral. We just learning from the professor also want in the University of Poitiers. Because the project is supported by the Honda, the company. So almost about 3 years. I think most people know about the fuel cell or the electrolysis. So we need the high efficiency, the no noise, the friendly environment. But the problem is the oxygen electrode, the kinetic intuiting sluggish. The primary catalyst by the pressure meter, the palladium, ruthenium, uranium. High cost at the very low scarcity or time-dependent drift. So we need, although we hope it's probably to develop low cost and high activity and longer durability and stability for the oxygen electrode. Otherwise, our work on this one. About the lead double hydroxide, I don't know most people know this one or no. But lead double hydroxide is naturally it's a mineral, and it's very about 1884 in Sweden. But after it's a very nice one. It's very easy to synthesize in the laboratory, in the factory. It's about it's a host, it's 2 part, it's a host sheet or in the region. So we can choose It's very easy to tube the chemical composition in whole sheet, or the internal anions are interchangeable. The different type of chemical bonds occur in the structure. The host gas or gas and gas are ordered arrangement. It's very nice and sandwich. So we can change the host sheet or change anions, internal anions. So that's why it's also a family. It's not really one kind of chemical product. So in the group, is one the professor done. Is one the academic, the fellow in China. About RDH, so we can to change, to modify the transformation. So we change how the host near converted to mixed metal oxide, MO, and internal gas turned into its derivative under the heat treatment. So we just heating, we can get different structure, different duration. For example, the regulation of net composition. We can modify the coordination environment and electric structure of active. The sides or inclination, we can enlarge the basal spacing and expose more inner active size. Also, we can the build and constructure the vacancy engineering, the oxygen vacancy and metal vacancy to facilitate the absorption of reaction intermediates. Also, we can develop European nanostructure to increase the disposed number of active age sites. Also, we can do hybridization to enhance the electric conductivity and provide multifunctional properties. So the RDH is for electrocatalyst, for the polymer additive, and others. So there have in their group the set of key laboratory CRE. The big group work on RDH. So we can check the papers. The very nice paper is published in recent year, or about 1 year, more than 1,000 papers published of RDH for the OER, oxygen evolution reaction. So nickel, especially nickel iron and copper, the iron and others. So we can share this one. Also, it's for the oxygen reduction reaction. Also, it's bifunctional, the oxygen evolution reaction. So we can design the chemical composition, design the structure, and design the metal oxide. Also for the oxygen evolution, so many papers published about on the RDH and developed the no pressure electrocatalyst. So different model, different morphologic, and different the shape and others. So in my small group, so work on the no pressure electrocatalyst. So one term is copper oxide. Also is from RDH and the multi-ride copper nitrides and the carbon. Also near the double hydroxide. Also is carcinides. The one is beginning I from the University of Poitiers is work with the operator also want. So here in today I just show some example of RDH. How do the electrocatalyst? The first one, we can change the net composition. In nature, the RDH most is Mg and aluminum RDH, but we can change other chemical composition, the carbon Mn to the host sheet. So after we can calculation to this point to the mixed the metal oxide. So the carbon oxide amine oxide and RGO together for another composition to derive from the LDH. So here we can show it's very nice the electro interaction between the carbon oxide and amine oxide. So this one is why we can develop about the oxygen reduction reaction. So the one show is very nice. The oxygen reduction performance in arcanide electrolyte, and the resulting from the synergistic effect between carbon oxide and amine oxide. So we can shift different electrochemistry because in both sides it's very nice higher dispersion. That one be different from the you synthesize from the others to the chemical the synthesize. So that LDH is a precursor. Or other one we change to the nickel, the carbon nickel amine for the host sheet. So that means the ternary of carbon nickel amine LDH, and also with the polymer PPY together and fabricated by the one step involving formation of the LDH, and then for the polymer memorization of PY. Also the LDH, another sheet, is the vertical the groove on RGO to support. So we can get a very nice dispersion, very nice the conductivity. So also we derived to the excellent bifunctional oxygen reduction reaction or oxygen evolution reaction, the bifunctional activity, and also durability and stability in alkalite. So here we show about the 18,000 seconds and show about 90% is remain, and also more than 1,500 the circle, the CV circle, show the stability. And the other one, because LDH is also the porous the materials, so we can some organic we can absorb on the surface of LDH, and then we can calcinate under the nitrogen atomers. We can produce the carbon the nitride on the support. Also inside is nickel iron the spinels. As we know, the spinels is very nice for their oxygen evolution, and the carbon the nitride is for their oxygen reduction. So we can one compost, we can produce the bifunctional the electrocatalyst. So here we show just a series of carbon PCTS is absorbed on nickel iron LDH, the precursors, and then we produce the different the catalyst under the calcination. So we can get different contents and different the species in the compost. For example, there are different 9 species. So we can change and modify the different the type of nitrogen in the compost, and then we can change different the electro activity. So we can see here we just show absorption of copper PCTC on the nickel LDH, so we can significantly enhanced electrocatalytic performance as compared with the physical mixture of PCTC and the nickel LDH. So that means the between compost, we can get some synergistic effect between 2 components. So that is why we together. So other one, in the beginning, we just show the absorption of the organic on the surface of the LDH. We can intercalation the organic internet the regions. For example, here show the SDH, nickel iron SDH is by anion is a chain reaction to the internet space of RDH. Then we calcinate to produce the both composition. One is the nickel iron spinner for the oxygen evolution reaction, and the other one is the copper nitrate to the oxygen reduction reaction. So here show one the example. So we can get two the active centers. One is for oxygen OR, one is OER. But both sides in one in the compost is very nice. The high dispersion of catalytical societies. That's why it's the RDH. So we use RDH, we get very nice the dispersion of different the catalytical societies. And also we can change, we can see the IG is a higher gravitic the degree and larger disordered the carbon domains. And then we can by the pressure, the confinement effect of the RDH. So we can produce the high increased the content of carbon, nitrate, and with nickel and gravitic 9 species. So we can get very, because the ones located in the internet species. So after we calcinate, we get it is higher the contents, higher content. So also is for the oxygen or oxygen evolution. So we get a very nice excellent the bifunctional the oxygen reaction performers. So the difference evolution is about 0.84 in alkali intermediates. So we see just one is by the half cells. After we get nice regenerative the micro fuel cells. But this one we work the one in the University of Poitiers is for the collaboration with Professor Alonso Wang. So here we show the no pressure the electrocatalyst is compared with the platinum. The show is very nice or reachable by functional activity. It's very close to iron, oxygen, carbon, and out the performer platinum carbon. So we get very nice remote stability in alternative the modes in the using that regenerative the macro fuel cell inside. So we make the 3 circles almost is stability. So the one is already published in the general part size. And also we can make the non-structured about the nickel iron RDH is hollow the macro the superior. We can fabricate by template free the hydrothermal method by adjusting the concentration of fluoride, the meteorite, the fluoride. That means we get the hollow sphere of RDH. As we know, the RDH generally is the is nerd and nerd the pinate. It's difficult to get the sphere. Here we just show the 0.5 the molar. It shows very hollow the macro sphere of energy. And this one is about the thickness about 1.02 the micrometer. So that we get the ones for the oxygen evolution. So we can see the at RTM we get very nice the hollow. So we think about how to perform. We can first with the beginning the nickel oxide and due to hydrothermal method we get the new patterns. and then we define the time, depending on the time, 4 hours, 8 hours, and 12 hours. We get hollow the regions. Then after different inside different thickness and different hollow species, we can get different the oxygen evolution, the performers. So we can compare to the one with the solid, the one. So here we can see the almost is comparable to the commercial, the ruthenium oxide. So another one, we change this RDH here, the in situ, the growth under the carbon, the fiber. So here we just show the one, the fabric, carbon fabric. After we can absorb the nickel, iron, the ornanins, the nins, and anars, and then we can produce the RDH. Here we just change the different controlled or more the content of SDS. So the different SDS, so with the collection to internal regions, so we can get the different the internal the space. For example, we change 0 to 1.5. From SRD, we can see we can get the different the surface area or the pore width or pore volume. So that means we use SDS as an internal spacer agent to enlarge the internal distance and increase the specific area. So we can change the different part like the part size and change the internal the region. So here we can get the morphology. We see the very nice. The like the orange, irons. The RDH is on the non under the carbon fiber. So we can change the ratio and change the morphology. So after we can see the different the evolution, the reaction performance. Here he show the lower the over potential and we lower the technical slope because the different the internal distance of RDH, then the many is enhance the surface and accelerate the dispersion. So one is another structure, and also we show others on a topic of the conclusions. Because we how to for how to design the RDH. The first one we how to design the layered composition. So we can arrange and change the host sheet. For example, the nickel, the iron, and others. And also we can use exfoliation RDH but into nano sheet. Here I don't show the nano sheet, but really we can do the nano sheet for RDH. Also, we can make the constructing the 3-dimension hierarchic nano architecture of RDH, like the hollow, the sphere. Also, we can get host gas interaction. We can change the RDH, the composition, the morphology, and others. And then we can show the different the chemical composition. Also, we can change the absorption. So in just beginning about RDH, so we can develop and produce the both of promised RDH of oxygen reduction and oxygen evolution action with different structures, the chemical composition, and in strength, the synergetic effect. So we can increase the number of active studies and improve intrinsic activity of each active site. So that means we based on RDH. So that means, so we can develop, because RDH like the template. So we can in the hot shade or in the internet species, we can develop the different composition, morphologic, and others for the electrode catalyst. Especially now it's for oxygen evolution. It's many paper and many is published on LDH. But this one is very others in the laboratory. It's okay. So we want to develop scalable synergetic method. So we prepare LDH, the best electrocatalyst with satisfactory activity and structural stability, and the performer to achieve the post-production and large scale application. In our group, we produce in a factory for 1,000, more than 3,000 tons per year for LDH to the polymer additive. For example, for PVC, for the PPP, it's okay. But for the electrocatalyst, now it's really just in the laboratory because there are the performers and there are active, their stability is not very. It's not ready for the really practical application. And other one is very difficult to identify the real active size and the product reaction, the mechanism. That's why sometimes we are collaboration with the Professor Lucy for the calculation, how to define the real active size. Because LDH has a more communicated chemical composition. So generally we need to resolve to different technique to see what happened inside. So it's not easy to buy the techniques. And others, we need the chemical and mechanical stability, because LDH is like the powder. So how do we develop and enhance the LDH-based electrode under industry condition, such as strong alkaline electrolyte, high operating temperature, or high current density? So the other one, so it's a little complicated. It's difficult in the for the LDH. But also we have some group to develop the LDH for the electrolytes in in like ocean, in the high the salt, the water. So that means it's on the road to develop for the LDH, for the electrode, the catalyst. So all the work is supported in the state key laboratory of chemical resource engineering. So the ones are just one more than 10 the teams in this key laboratory. So more than 30 professors and more than 300 students, the master and the PhD in the laboratory. So modularly we work on the LDH and work on the polymer and work on the catalyst. So we need to develop the different chemical, how to efficiently use the chemical resource. Because I don't know, in China we have the very nice the salt lake in the Qinghai, in the west of China. So the chairman Xi, we want to build the water near the salt lake. So we need more work on here. Otherwise, the most funding is from the National Natural Science Foundation and the Basic Research Program of China. Because in this year in China have pay a lot of funding for the science, the scientific research, or for the or collaboration with the company, so the funding. Also with the Beijing Engineering Center of Hydroxides Catalyst. because this one is especially for the catalyst. And also we collaboration with Professor also want and Professor Lucy. So for the electrocatalyst, we have, because beginning before I did my postdoctoral in the University of Poitiers, I never did electrocatalyst. So the one I just beginning my electrocatalyst from 2017. So beginning I just work on the RDH. So after we work on the electrocatalyst. Also is 2010, I come back to Beijing to BUCT. Also we follow the electrocatalyst. So we use RDH to develop some the catalyst. So also we not use all the members in the team. So for the PhD and the master. So a little different in China. The master in China about 3 years. So about 1 year or half a year is for the lecture, and others is just work in the laboratory. So this one is only little difference from the I don't know them in Mexico, because this one is different from the France. In the France, the master about 2 years. In China, it's 3 years. So almost like a PhD. Of course, the ones the work, the report is only the difference. Also, in the PhD in China are about 5 years or 4 years, 4 years to 5 years. So we can collaboration with the government support to outside, so we can work together. So also it's very common. So for the collaboration in Mexico or in other place. So as I remember, there was some funding between the Mexico and the China government, and also others. We can get their collaboration to develop as we design some high performers, their catalyst, and others. So here's my information for the one for their email or their researcher ID. So we can check in their website what we have done. And also we some papers and some others. So anyway, so we want to develop based on RDH is for electrocatalyst, for the polymer additives and others. We want to use the RDH and then to do others, the practical applications. Okay, thank you for your time and for thank you very much.
Thank you, Professor Feng.
Thank you very much, Doctor. Excellent presentation. Bueno, vamos a pasar a la sesión de preguntas y respuestas. Les aclaro que pueden hacerlas a través del chat de la transmisión en YouTube y les solicitamos, por favor, que nos digan su nombre y adscripción o lugar de origen, por favor. Le cedo la palabra al doctor Luis Estudillo, por favor.
Okay, gracias. Thank you, Professor Feng, for your presentation. It's very impressive to all the work that you are working on your team or developing in your team. We have a few questions for your presentation. The first one is, how affect the morphology of the materials of the LDH materials in the improvement of the fuel cells?
The morphology of RDH. That means generally that one the painted. So we modify the surfactant, the template, or free template. We just for the control the concentration of the metal, the concentration, and also we in our group we have special the reactor to synthesize RDH. That we is special one. We more than 20 years. So in the group special the reactor.
Okay, I saw that the morphology is important. You show a nanotubes. With this nanotube, you can improve the stability on the application in fuel cells, Professor.
Yeah, because you different morphologic, that means you use different part structure, so we can deploy the different active sites, and we can active more. The active side is to the reaction. So that means also we can adjust the internet space for the diffusion, and so we can modify modify the morphologic, so we can get the hard the surface, and it can enlarge the pore, the diameter. So the one very nice. We can very carefully to trim the morphology of LDH.
Okay. Okay, we have another question. Professor Feng, what is it's important to the relation between elements that you try to dope. I mean, dope is a kind of word that we can use. The LDH materials. It's important to quantify the relation between two elements. For example, in the nickel iron, the relation between the substrate and the iron is important, right? How do you? It's important to change this and the application that you can do in the fuel cells.
You mean we change the nickel, the iron, the chemical composition, or is because in the LDH how the sheet, so we can not red. So we can choose different about the metal. For example, the nickel iron is 1 star the valent, 1 is the trivalent. The metal the anions in the whole sheet. So the ones that we can choose, we change. But from the literature, so we can say the nickel iron LDH almost the best one for the oxygen evolution.
Okay. Dr. Alcantara, have another question. I think it's another question. Yes. If we change the element, for example, nickel iron for others no precious metals, you can find a little bit improve the stability of your materials, or just nickel iron is the best for now?
No, up to date, to say the nickel iron LDH is very nice for the oxygen evolution reaction, but also we can change it to the copper, aluminum, and the copper, the nickel, and others. All the people that working on. But the till now we just say the nickel iron LDH, nickel 3 iron LDH is very nice for the oxygen evolution. But we hope we can develop the bifunctional oxygen electrode. So we now for the in the group, so we work on the copper aluminum. After we can etch the aluminum, so we can the beard the recantancy about the whole sheet. We get there, for example, for the carcinide, the cobalt, and the others. So just we can design the just use the precursor. We can design to others electrocatalyst.
Another question, Professor. Do you found some clues about the interaction between the LDH materials with the support? Because you show that you combine LDH with RGO. So this interaction is important, or you can find, or there is some clues that show us how the LDH interaction with the RGO is important in these applications?
Because the LDH is like the main hydroxide, so the conductivity is not very high. So we need the carbon support and or RGO to increase the conductivity. So that's why we disperse. Also, the disperse the RDH is in RGO. So that means that we can get in control the dispersion. So we can in both sides. So we use the RDH to combine it with the carbon oxide, the active carbon or RGO and other carbon. We can increase the conductivity.
Okay. So these materials, Professor, you try to use in HER, hydrogen evolution reaction or hydrogen oxidation reaction. Did you try to put this in the performance on these reactions? I mean, your materials try to use in another reaction in fuel cells like HER, for example. You try it?
Till now, we not show it. We not change. We usually use the oxygen, with oxygen electrolytes. Yeah, it's for the oxygen reduction reaction and oxygen evolution reaction.
Okay. Okay. Thank you so much, Professor, for all your response. Cedo la palabra al doctor Alcántara. Si tenemos alguna pregunta, me dices, ¿no? Si no, bueno, adelante.
No, creo que ya no hay más preguntas. Bueno, con esto damos por concluida la sesión del día de hoy. Y bueno, daré lectura a la constancia digital, profesor Feng, misma que pues haremos llegar vía correo electrónico, ¿no? We will send you via email, Professor Feng.
Okay, thank you.
Bueno, la Cátedra Patrimonial en Medio Ambiente, doctor Héctor Mayagoitia Domínguez, en su 6ª edición 2021, certifica al doctor Yongjun Feng por su excelente presentación, High Performance Oxygen Electrode Electrocatalysts Derived from Layer Double Hydroxides. Esto es como la Cátedra Patrimonial en Medio Ambiente, doctor Héctor Mayagoitia Domínguez, Excellent Professorship and Environment Science, Mexico City, 11 November 2021. La técnica al servicio de la patria, firmada por el doctor Víctor Florencio Santés, director del CIIEMAD. Thank you, Professor Yongjun Feng.
Okay, thank you.
Y bueno, les recordamos a nuestros asistentes que la próxima y última sesión de la Cátedra Patrimonial Héctor Mayagoitia Domínguez en su 6ª edición, la cual será llevada a cabo el martes 16 de noviembre a las 11 de la mañana. Nos acompañará el doctor Víctor Vilar de la Facultad de Ingeniería de la Universidad del Porto con la conferencia Reactores novedosos para los procesos fotoquímicos, fotocatalíticos y fotoelectrocatalíticos hacia la intensificación del proceso. Recuerden que estas sesiones quedan grabadas en el canal de YouTube. Los invitamos a que se suscriban y nos sigan en redes sociales. También, igualmente, les recordamos a los alumnos BUCT y personas interesadas que puedan solicitar su constancia de asistencia de acuerdo con los parámetros que se encuentran en la página web del evento. Sin más, les agradezco mucho su atención. Gracias a nuestro panelista, al doctor, y a todo el equipo del CIIEMAD que hace posible esta transmisión de estos eventos. Excelente tarde a todos. Gracias.